as we all sort of been living through this sort of revolution, if you'd like, in machine learning applied to image processing, I am constantly amazed at the breadth of applications that this technology can be applied to, areas that I've spent very little time thinking about. And our next speaker is going to talk about one of those areas, which is mining. It was never my objective to ever be a miner. That was never in my career paths. I'm not exactly what Ravi's doing, but the whole mining space is pretty interesting and certainly important, and he's going to talk to us about that. So next up is going to be Ravi Sahu, who's founder and CEO of Strayos. And he's going to talk to us about how the challenges and application of machine learning, 3D machine learning specifically, to the area of mining. So pretty interesting topic. Come on up, Ravi. Thank you.
Thank you. Thank you. My name is Ravi Sahu, and Strayos, as Strayos, we started the company about 3 years ago, looking at the problems in the, not so the industries which has always been overlooked, like mining or heavy industries. And I was fascinated by the problems and how vision and AI would benefit in these industries, because mining is one of the constant moving factory, which is always collecting data. And this data is these data sets are very interesting data sets that you can't access outside of the mining sites. So today I'm going to talk about one of the basically the use case, how we can make the use of these data sets and apply machine learning, combining the vision data to make mining operations more effective. So let's just jump right in. So just as an outline to what we are going to cover is we're basically targeting going narrowly on one use case. What are the better ways to extract features from the mining terraneous data? So where you're looking at just the rocks as well as the cliff slope. And then other than that, there's basically no other feature sets are there. Either there's this terrain are usually just, one specific colors are there. Either it's a very brown or black colors are there. And you're trying to understand the geology there. So we picked that as a use case. What type of techniques, segmentation technique, will work effectively if we have to analyze, point by point features here. So that's the use case here. And then we'll look into the data acquisition method, how the data gets acquired, and then various other interpolation and subsampling techniques that has been used, as well as the challenges that we faced in the feature extraction process, and how do we train the neural network to scale this model for thousands of projects that happens on a mining site, and the future work that we are currently working on as well. So the use case really kind of focuses on what segmentation technique that should be used for mining-related operation, and how, because the mining is a constantly moving factory and the scene is constantly evolving, so how do we better understand the scene, what has been operated today, how it will impact the next day or next few hours. So that's one of the key insights that we are trying to extract using the imagery data. This helps in understanding, if we choose a proper segmentation technique, we are looking for the geometry as well as the geology data. So at the end of the day, the segmentation will help you determine how to better drill, how to better find ore deposits, and also plan the overall mining operations, like how to better design the routing system to move the trucks out, and do various inventory calculations which are there in the site. But more importantly, every mining site, what they are looking is if they are collecting vision-related data through the imagery or any other sort of vision applications, the number one thing that they are looking is how do we improve the safety in the mining site, which is their primary concern if the data has been collected on a daily basis. So just kind of talk about setting the base for the segmentation techniques here. There are various great ways of doing the segmentation techniques, to separate objects. We looked at, before jumping onto the actual 3D machine learning and the texture mapping descriptors that we have. The techniques like k-means, clustering, which is basically kind of looking into grouping the objects as well as, and then finding, what's the roads and what's the other, dimensions are there, and basically finding a distance metric. And then also looked into the graph partitioning as well, where it's just kind of grouping all the nodes, a variety of objects, and whether this will work or not. And then also looked into the mean shift segmentation to finding the local kind of homogeneous area or space, and then grouping and segmenting them. But all these techniques didn't work properly to get to the level of accuracy that we were looking for the mining-related data sets. So similarly, the problems that we faced is, because the mining terrains are so, sometimes it's just so flat, and sometimes it's very, the slopes are not, properly, there is a very roughness roughness dimensions are there, and the areas, the geology and the inclination factor. So all these segmentation techniques were only getting to the level of accuracy it's just not usable. So that's why we shifted into a different ways of doing the segmentation here. Well, let's talk about the data acquisition process here. So this data was especially collected through the UAVs, basically drones. Our previous speaker kind of mostly talked about collecting a vast amount of data through the satellite imagery. Here we are dealing with, in the mining site, kind of going more regional specific or site specific. So they are looking at up to a centimeter per pixel level types of data quality to make more better decisions at a granular level. So the acquisition process, the drones were used, a specific flight path, and then collected images at a different camera angles. So as you can see, this is some of the image sets that we have. It's kind of collecting an area where there is a area where the material has been basically pushed out, blasted, and also there is another high wall area where they're trying to understand the planning process. So we will use this data to further kind of expand and build our use case here. So this now the processing steps. First we took this data. So we have data collected, imagery from different angles and different positions. So each image also captures various other geolocation information. So this image has metadata in the form of basically EXIF information, which has altitude, latitude, and longitude information, and a variety of really rich information related to the camera parameters, focal length, and So we are using this to process and generate a model here, more accurate model in terms of the 3D layer here. So we used these data sets to process and stitch together this information and convert into a 3D model, which is applied through the stereo motion technique, like you might have heard from in structure from motion technique. So we use that to generate this 3D model. And the reconstruction, at the end of the reconstruction, we also received a dense point cloud. So dense point cloud gives a more positional XYZ information, which is very accurate information for doing a lot of geometry and geology analysis for the mine development, exploration, and mine planning purposes. So that's what we are looking, instead of just the true segmentation or the classification technique here. So this is the processing part of the data. Just going into a little bit more about the stereo motion technique. So as you can see, these are just exactly the two images it looks like, but it has been taken from a different camera positions. So if you see, this is one of the images on the your right-hand side, which has the complete area of the high wall is there, but in the second, you are seeing a much more closer cliff there as well. So it's basically kind of collecting the features at different positions, which we call the key point. So the same camera angle has been collected various key point features, and each key point has model, camera model, focal length, and various other parameters here. So we use this, all the information to generate the model, and this gives us the more precise positional accuracy from the geometry perspective. So so we're still in the processing phase here. We received various different types of outputs. So one of the outputs is triangulated mesh, which is also OBJ model, object model here. And this triangulated mesh is basically connected, with the adjacent boundaries, 3 points, which has various, precise vertices are there. And these vertices are seamlessly, connected to each other to form a complete, model that can be utilized to further expand the geometry knowledge for that particular mining site that we have seen for further planning purposes. And it's also this OBJ model can be further subsampled to understand various density-related information, and various other measurements can be done on top of it. So as you can see in this model, if you see one of the, it's so dense that it's kind of almost looking like a black colored model, but if you further zoom in and zoom out, you will see these are all connected to a vertices, which is looking at so dense here. So these are very precise, up to a 0.7, up to spacing is up to a 1 meter, but 0.7 centimeter, which is really going into a very minute details about each specific material properties here. So coming back now, the processing has been done where we received our model outputs, 3D data, OBJ model, and the point cloud data. Now we are going to see about the feature extraction process here. How do we use this data, the OBJ vertices information, the XYZ, and the point cloud XYZ as well. So one of the procedural steps, there are various procedural steps here, but there are no good way to train the model for the point cloud related data here. So if you use the traditional segmentation technique, it goes by patch to patch or pixel to pixel. Here we are adding an extra element of point information, like to get to the level of accuracy. So we have to develop various other invariant features for this model basically. So kind of describing multiple features was one of the steps that is required to classify just different surfaces here. So can we define whether there is a greenery there or not, or roads, or whether that material was actually a hard rock or it's a soft rock, or sand is there, or more of a refined rocks are there. So those are the things need to be picked up when we are doing the feature classification. So we wrote a frequency texture descriptor here, which actually captures each point by point the roughness, the curvature, and the normals of this type of information, which couldn't be captured just looking at the pixel values here. And then both components are kind of in the Cartesian and RGB space, so it also gives us the information from both perspective. So what this provides is it provided very high discriminability of the surface information and the textures that with the positional information as well. So that gives now we are combining what's been classified, what's that particular feature is, along with the normals and the curvature of that particular object there. So the challenges that we faced in the feature extraction process is, as you can see, if you go back to one of the images that we saw, the OBJ file, the model, were generated using number of images, and in that case, it was roughly about 120 images, and each image has roughly about 30 about 30 MB, each image is 30 MB data, and 2000 by 2000 dimension size, data points are there. So it has a high detail there. But the triangular mesh lacked points kind of, on the low curvature side. So we found the normals and the curvature properly, but if you're going around the edges, that's where we are losing the quality of this, mesh as well. So the segmentation in basically the 3D space requires, a lot of like dense point cloud analysis. So that's we use now not just the OBJ method. Now we are bringing the point cloud related information where we lost information from the mesh file here. So we started interpolating both OBJ file and the point cloud information that we have, which also has the similar XYZ information. And we use basically barycentric coordinate method, which kind of gives you the simplex information about if you are looking at tetrahedron or triangle, it gives you the center of mass from that particular objects that were there. So why is it important? Because we are looking at the geometry, and we are looking at where that geometry is evenly spaced out in the 3D environment. So as you can see here now, we added on top of OBJ, you can see the point information. So each granular points that you're looking, it's a point cloud data. And you can corresponding RGB value can be also extracted from this point cloud information here. So each point has about roughly 0.25 units with a uniform density that we subsampled for the further analysis to train our neural network. This is kind of going in detail. As you can see, this is area where there's loose rocks are there, but then instantly there is a flat surface. So you will see that in the flat surface, the point density is lower now. So that gives us a good information that how to analyze the roughness and the density for that particular area. And then we assigned normal at each point after the interpolation, and then also the curvature value were identified for these points, and we basically kept assigning the bounding box for each point here, which gave us the orientation for the each associated spatial information as well. So combining all this, we kind of created a neighborhood for each point cloud, for each point in that point cloud file. And this neighborhood, now we can project basically downwards in the direction to the normal to generate more localized patching of this image. And that kind of leads to a further more accuracy related quest about the geometry here, because now we are getting to the level of taking that point and generating the localized image patch. So that's where the results kind of came in, which basically kind of segments now the feature. Basically now we have identified the features, and now it has started to interpolate and gives you the information about utilizing this neighborhood patching that we did. What are the predominant frequencies are there? And we assigned them into low, medium, and high bands, and color coded that. And that each bands, now we can assign the texture value as well, and the Z value, which is coming from the point cloud data. So as you can see, the larger areas where there's rocks are there, and then the loose rocks are there, you will see they are in blue. And then the just local flat surfaces, rough surfaces are there, they are in red here. So the 2D texture kind of gives a variation for each color and each point that were also further used for the training as well. So now we look into the machine learning part here. What we basically did with this data set. So we've got the neighborhood information and the point information XYZ. So how do we use this to train the neural network? So we built a 4-layer, CNN here to classify features, here to predict more accurately for the further, projects and data sets about, where the rocks are there, and more importantly, where the blast area and the drilling area should be, to properly drill and extract material. And also where the nearest cliff is there, and what's the dimension of that cliff from the drilling machine should be, and where the roads are there so that to effectively transport the material after they blast that area or the material there after the material extraction has been completed. So this classified kind of points that were taken. We did a clustering, grouped them into the categories to understand basically the scene of that mining site. And the point information were labeled and then passed on into the CSV file for the training the network here. So this is kind of the architecture looked like. So it's more, right now it's kind of convolutional, but now we have developed fully convolutional as well. So it's kind of categories that we were labeled: rocks, cliffs, drill holes. Drill holes are very small, diameter, so and also associated with the geometry. So that's why the point information was very crucial to get to the accuracy. And the blasted area, the high wall geometry, the geometry looks like if they are extracting this material. So there's total data set. The size of our first used for the training was about 22 gigabytes. And the approach that we took to label the data set was manual. And in some cases, we also used custom scripting to automate the labeling part as well. So the performance of the neural network on the trained data set that we used, 3 trained data sets, we used about 400,000 points, after interpolation and desampling, and the 30 to 40% points are kind of labeled, and masked manually. So that means obviously you will get a higher accuracy there because somebody who is coming from the mining domain, they were labeling it, basically our users and customers, and then we trained this model across various these 3 data sets, and we received a really high accuracy, about 99.7%, to really identify where the blast hole is or the drilled hole is, and where the specific cliff geometry is there. But the trained model that we, after that model was trained, we used it on the test data sets, the same network, so it's roughly about 90.2%, so accuracy was definitely dropped there. Some of the results kind of came, as you can see, this on the other data set, similar mining site area, their drilled holes are there. So it classifies basically where in the red region, it's, as you can see, the point information, which has the geometry associated, and also it's understanding the geology. So it identifying all the red colored information is cliffs and the slope. And the estimated area is roughly 25,000 square meter there. And similarly, the green is roughly a road which is passing by. And the blue, which is roughly an area which is basically the safety wall is there. And the yellow is the entire area, which is the blasted geometry is there because the drilled holes are there. So from the conclusion, what we have it here is when we look into the just the traditional segmentation techniques, we are looking here the mining data sets. We have just the terrain-related information and not high degree of feature variance are there. So an understanding the geometry and the geology requires more going and using the data sets like OBJ or the point cloud data, which gets to the level of the segmentation for the geometry as well. So the techniques of neighborhood localized image patching were much better in this case to get to the level of accuracy. And the scene as understood right now as in the model can be further analyzed to draw various safety conclusions. So if there is a mining area and we have blasted and extracted the material, how soon we can send the crew to clear that, or whether there is a big rocks there or loose rocks are there, so that we make proper, more effective decision about, from the site manager perspective, that this is the area you should not be moving your trucks. So again, the safety decisions can be made very precisely and accurately. So the application of machine learning in the mining industry, as you can see, that's really tremendous benefits are there, because the data is really unique, and if done right, the applied AI here, they're seeing the benefit and the impact immediately. So in this case, they were really able to optimize the geometry of their entire blast area and how effectively they should mine that particular regions. The future work that kind of is going is detecting more anomalies through the image processing pipeline that we have, as well as how to make this more accurate and more faster. One of the future work is also we're working towards how do we use this to not only provide the insights at what has been drilled, or the more future applications where how effectively it should be drilled, but also identifying the ore deposits. So if this is an area, whether what type of ores are there, whether it's a block of iron, or whether there is other waste materials are associated along with it. And then separating the minerals and the waste rocks as well. So that's the future work that we are currently progressing, utilizing the same model here. So yeah, that's all I have. We are in booth number 807, so would welcome you guys to stop by and look at the demos over there.
Ravi. Very interesting. Was that, maybe I missed this, but is it all drone video or footage that you're working off of?
Yeah, so all the data sets that we had it here, it's all through the drone imagery.
So industrial drones flying over?
Yeah. And in some cases, we also receive the imagery from the machines. So like big bulldozers or drill machines, they have a camera mounted on the equipments, and they send us the images as well.
Okay, if anyone has any questions, by the way, there's 2 microphones set up right in the middle of the room there. You make your way to the microphones. That'd be great. Question, yeah.
Hi, so the fun thing about looking at rocks, as you said, is they all kind of look like the same color. So in addition to the texture mapping and classification that you did, were you able at all to pull in any visible data and help with your classification, or is it just kind of, you'd lay that on top as another layer to your model?
Yeah, that's another layer on top of the model. So like looking at the actual geometry of the rock, and then if there is another layer is there, so we are identifying other types of distinct features, how each rock is looking different and separated from each other. So there is a dimension of basically small rock and the big rocks, and how they are closely associated with the neighborhood localized patch, and we are using that information to separate it out.
Any other questions? Microphones are up. Great. I guess the silly thing is, your future thing is you're going to start looking at actual minerals.
Yeah.
So you're literally talking about being able, from a drone, being able to tell what type of minerals might be available on that site? Is that outside the realm of possibility, or?
Yeah, so we are combining now the other data sources, so just the imagery as well as when it's actually drilling. The real time, the drill sensors are also sending information. Sure. So we're combining that data to really going into the geophysical level to understand, and then we're building basically geotechnical algorithms to understand whether that hardness that is there, that attributes to an iron ore or copper. So that type of analysis.
Fascinating stuff. Well, Ravi, thank you very much for your presentation.
Thank you.